Hello guys, I'm really glad to see you back again. Today we will learn our first integration technique, one based on chain rule. Today we will learn integration by substitution. Let us consider the following integral. The integral of 3x squared times e to the x cubed dx. How do we solve this integral when there's no such thing like the product rule for integrals that allows us to say that this particular integral is equal to the integral of 3x squared dx times the integral of e to the x cubed dx? Now notice that the argument of the function e to the x cubed is x cubed, and is such that its derivative is part of the integral because the derivative of x cubed is equal to 3x squared dx. So if we call u equals x cubed, then du, the derivative of u, is equal to 3x squared dx, which is part of the integral. So we can substitute these variables for transforming the integral of 3x squared e to the x cubed dx into the integral of e to the u du, which integral we know because the integral of this is simply e to the u plus c. But now we have to return the change of variable. Remember that u is equal to x cubed. So the original integral will be equal to e to the x cubed plus c. Let us try to generalize the previous example into the following statement. If h represents an antiderivative of the function f and u equals g of x is differentiable, then the integral of f of g of x times g prime of x dx will be equal to the integral of f of u du, where du is equal to g prime of x dx. And this is called the substitution technique. Let us consider several examples for understanding this result in a better way. The integral of x squared times x cubed plus 1 to the 5 dx is an integral such that if we consider x cubed plus 1, its derivative, it's almost there because the derivative of x cubed plus 1 is 3x squared. We're lacking for that 3. So something that we can do is multiply and divide by 3. And we end up having the integral of 3x squared x cubed plus 1 to the 5 dx divided by 3. But we can take this 1 over 3 outside the integral due to the linearity of the integral. And now we can perform the substitution. If we say that u is equal to x cubed plus 1, du is 3x squared dx. Thus, the original integral becomes a third of the integral of u to the 5 du, which is equal to a third times u to the 6 divided by 6 plus c. But if we return the change of variable, we have that the original integral is equal to x cubed plus 1 to the power of 6 divided by 18 plus c. Let us consider the integral of dt over t natural logarithm of t. If we do u equals natural logarithm of t, its derivative du is equal to dt over t. Thus, the original integral becomes the integral of du over u. And this is equal to the natural logarithm of the natural logarithm of t plus c. Now, if we consider the integral of tangent of x dx, we need to rewrite this one as the integral of sine of x dx divided by cosine of x. And if we do u equals cosine of x, its derivative, du, is minus sine of x dx. So the original integral becomes minus the integral of u to the minus 1 du. And this is equal to minus the natural logarithm of the absolute value of u plus c. But if we use properties of logarithms, we have that this is equal to the natural logarithm of 1 over u plus c. But u is cosine, thus the final result will be equal to the natural logarithm of the absolute value of 1 over cosine, which is secant of x, plus the constant of integration c. Now let us solve the integral of the square root of 4x minus 3 dx. If we do u equals 4x minus 3, its derivative, du, is equal to 4 dx. Now we need to multiply and divide by 4, and now our integral becomes a fourth of the integral of the square root of 4x minus 3 times 4 dx, and we can perform the substitution. And now we have a fourth of the integral of the square root of u du, which is the same as a fourth of the integral of u to the power of a half du. And this is equal to a fourth of u to the 3 over 2 divided by 3 over 2 plus c. And if we simplify and we return the change of variable, we end up having 4x minus 3 to the power of 3 over 2 divided by 6 plus c. In some cases, we use substitution for simplifying expressions that appear in the integral. For instance, when radicals appear in the integral. Consider the integral of z squared times the square root of 1 minus z dz. Now, we can apply substitution in the following way. If u is equal to 1 minus z, then du is minus dz. So we only need to multiply by negative both inside the integral and outside. But we also need to represent z squared in terms of u. So we need to solve for z in the equation u equals 1 minus z. If we do so, we get that z is equal to 1 minus u. And if we apply the proper substitutions, we get that the original integral is equal to minus the integral of 1 minus u squared times u to the half du. And if we expand the square, we end up having minus the integral of 1 minus 2u plus u squared times u to the half du. And after applying the distributive property, we end up having that the original integral becomes the following one, which is way simpler. Minus the integral of u to the half du plus the integral of 2u to the 3 halves du minus the integral of u to the 5 halves du. In some other cases, we need to complete the square before applying any substitution, like in the following integral. The integral of 8 dx divided by x squared minus 6x plus 25, which is equal to 8 times the integral of dx divided by x squared minus 6x plus 9 plus 16. And we can complete the square and have the 8 times the integral of dx divided by x minus 3 squared plus 4 squared. And if we do the substitution, u equals x minus 3, du is simply dx. And we end up having 8 times the integral of du divided by u squared plus 4 squared. Now we can factor the denominator by 4 squared, and now we have 8 over 16 times the integral of du over u divided by 4 squared plus 1. And if we perform another substitution, let's say z equals u over 4, then dz is equal to du over 4. So the previous integral becomes 8 over 4 times the integral of dz divided by z squared plus 1. And the integral of this is arctangent of z. Thus, the original integral is equal to 2 arctangent of z plus c. But we only need to return the change of variables, both z to u and from u to x, for having that the final result is 2 arctangent of x minus 3 divided by 4 plus c. Integration by substitution is quite a challenge, but not an impossible one to master. Try to solve the following problems in order to master this technique. And as always, see you in the next video.